Good morning, everyone. Welcome back from spring break. So we are starting a new topic today. We're talking about inequalities. We'll start out with one variable today, and then next week move on to two variables. But let's get started. All right, so today inequalities with one variable, and we're just going to go over some of the basics. So inequality basically is a symbol to compare. Equal sign is when two quantities are the same or equal in mathematics, and inequality, or we compare. I say -1 is less than 5. That means it's a smaller number. 3 is greater than or equal to 3. That's true because it is greater than or equal. -7 is less than or equal to -3. That's a true statement. 9 is greater than 0. The statement 7 is greater than 7 is a false statement because 7 is equal to but not strictly greater than 7. So what does an inequality with a variable mean? If I look at the inequality, x greater than 8. And well, x means that x is greater than 8, but really, qualities are straightforward. X has like an answer, one number. But for inequalities, many values can make this a true statement. X can be any number that makes it true. So any number greater than 8 is a solution to this inequality. X could be 9, 12, 20, 103, 10, 11, 8.5, or even just a tiny bit bigger than 8, 8.0001. The solution, the answer, is the set of all numbers greater than 8. We can show the solution set visually on a number line. The boundary value that marks the true statement from the false is at 8, and it's an open dot since x's number is larger than 8, but does not include 8. So it says, okay, there's my boundary value, and all numbers bigger than 8. And I know that that open dot means that the solution cannot actually be 8. Some basic things about the open and closed dot. I use an open dot when I have these like less than or greater than signs without the line underneath. That means that the boundary value is not included. And I use a closed point to indicate when it can be equal to that boundary value. So let's look at another example. If x is less than -3. X is any number less than -3. Our boundary value is -3. The solution set is all numbers less than, but not including -3. We sometimes say strictly less than. I have an open dot at -3 because -3 is not included. And I shade to the left because those are the numbers smaller, -4, -5, -6, because -4 is less than -3, -5 is less than -3. Those are all true. Even -3.5 is less than -3. But the other direction, -2 is less than -3. That is not a true statement. That's false. So to represent this next one, I have x is greater than or equal to -1. So x can be any number greater than or equal to -1. My boundary value is -1. The solution set is all numbers greater than and including -1. So there I've got my closed dot at -1 because it's included. And I shade to the right because those are my true values. -1 is greater than or equal to -1. -0.5 is greater than. -1. 0 is greater than or equal to -1, 1, those are all true. The other direction, I get false statements. -2 is not greater than or equal to -1. What happens when I have an inequality and the boundary value is not isolated? Here, this one's easy. G is greater than 3. Boundary value is 3. The numbers bigger are solutions. The numbers smaller are not solutions. And so it's a boundary value, so like 3.5, 4, 5, 6, 7, 10, they're all true statements. Numbers smaller, 3, 2.5, 2, 1, 0 are not and make false statements. What about something like this? 2m plus 5 is less than 15. Well, I could try out numbers till I find that boundary value. I'll start at 0, my favorite number. When I plug in 0 for m, 2 times 0 is 2 plus 2 times 0 is 0 plus 5 is 5, and that is less than 15. Yep, if I substitute in 1, 2 times 1 plus 5 is 7, that is less than 15, yep. And 2, I get 9 is less than 15, yep. M equals 3, yep, that's still true. M equals 4, I get 13, that is still true. And here, when I get to 5, wait, 2 times 5 is 10, plus 5 is 15. That is not less than 15. And if I keep going, I get more false statements. So 5 is my boundary value. It kind of separates the true statements from the false ones. And notice this boundary value happens when this is equal. 2 times m plus 5 equals 15 is my boundary value. So that gives us a strategy to do this faster. So we're going to isolate the variable just like it's an equation. So I'm going to add 4 to both sides first, and I get 3x is greater than or equal to 15. And then I'm going to divide by 3. And when I do that, I get x is greater than or equal to 5. If I was to substitute this back in, 3 times 5 is 15, minus 4 is 11. I see that that is an equal statement. For this particular one, so inverse operations work just the same. There's one exception we'll look at in the next example, that if we multiply or divide by a negative, we need to switch the sign. But other than that, I just use it exactly like an equality sign. And that boundary value is 5. That separates my true statements from my false ones. So if it's greater than 5, I get true statements. If it's less than 5, I get false statements. And I could always plug those in to check. Okay, the next one here, I have 5 minus 1 divided by 3 times x is less than 7. And I said 1 divided by 3, but that's also, we also say 1/3. I'm going to start isolating the variable. I'm going to subtract 5 first, and I have -1 divided by 3 times x is less than 2. So here I have to remember that this fraction is really division. So the opposite of that division is multiplication, and I need to multiply by a negative, and I multiply the entire equation. And when I do this, on the left side, -3 times 1, -1/3, that's +1. It becomes it cancels, it becomes a 1, and I just get 1x. And then on the right side, -3 times 2 is -6. And then I have to flip that inequality sign because I multiplied by a negative. So now my boundary value is -6. It's not included because there's no line underneath. It does not include -6. And I shade to the right because it's greater than. And I can always plug in some of these answers to check them to make sure. Last example, in this one, I have a variable on both sides of the inequality, and I need to get them together to start solving. So I'm going to get the variable terms together first, and then I'm going to start isolating the variable. I'm going to be careful on this one because sometimes if I end up with the variable on the right, I need to make sure that my statement, my solution is really about the variable. So first, I subtract 3m from both sides because I like positive numbers. And I get 4m minus 3m is just 1m. Then I'm going to move the 9 to the other side, -9, minus 9 on both sides, and I get 5 minus 9 is -4. So I have -4 is greater than m. My statement is really going to be about m though, so I need to know that really this is the same as m is less than -4. So when I do this, I have an open dot at -4, and then I shade to the left because I'm looking for solutions that are less than -4. So that sums up our examples for today. Good luck. Hopefully the assignments are a little shorter today, but enjoy the sunshine, and you'll be hearing from me soon.